systems of differential equations. Now here, I will assume linear algebra, since you guys have had it. If you haven't had it, oh well. So because you've had it, this is going to be pretty short. In fact, some of these things I already showed you guys in linear. But basically, we're interested in solving, I guess I should show you a little bit more. First of all, the first order problem suffices. Now let me show you what I mean by that. If we can solve the first order problem, a system of first order differential equations, that actually pretty much covers what's out there. So to give you an example of what I mean by that, suppose you had y prime prime plus 3y prime plus 2y equal to 0, and you had z prime prime plus y prime plus z equals to 0. Well, that's a system of two differential equations and two unknowns, right? Y and z, it's second order, both are second order. There's something called reduction of order that we can do. Now, it's not unique, but it certainly can be done. And so what we do is we just introduce variables, like I'll say x1 is y. Some of them will just keep the same. x2 is y prime. Now, with x2 being y prime, that makes my first equation become what? x2 prime prime plus 3 what? x2 prime prime? I'm an idiot. x2 prime, that's kind of the whole point. It changes the second derivative to a first derivative. 3x2 plus 2x1, right? Or equal to 0, or as will be convenient to us, that's x2 prime is equal to minus 2x1 minus 3x2. And of course, the first one, I also have, I can rewrite, I can write this one as x1 prime is equal to x2, right? So there's the first order differential equation, there's the first order differential equation. And then what else I do? I define z as x3, right? Let x3 equals to z, and let x4 equal to z prime. So from the definition of x4, we get that x3 prime is equal to x4. There we go. And finally, x4 prime, well, I'll write it out. x4 prime is z prime prime, right? I'm sorry. Yeah, okay, z prime prime, but that's equal to minus y prime minus z because of that equation up here. And let's see here, what was y prime? Was x, so that was minus x2, and z was what? Z was x3 minus x3. All right, there you go, that's x4 prime. So you see, I began with two second-order differential equations, and I've ended with 4 first-order differential equations. And you can always play this game to reduce order, to eliminate higher derivatives in terms of lower derivatives by adding variables. So this is called reduction of order. So for this reason, because I can do this, I don't want to prove it in general, but trust me, you can do it. If we can solve the first-order problem, we've solved all problems, right? So, and I don't actually want to solve, I mean, we could solve this, but I don't really feel like it. I mean, if I was actually going to solve this problem, I actually wouldn't use the matrix techniques I'm about to show you. If I was going to solve this problem, I would first solve the y equation, and then I would plug that in and solve the z equation.
Just solve for like y prime.
Yeah, I guess I could do that. It'll take a minute. This has characteristic values 2 and 1. The solution is y is equal to c1 e to the minus x plus c2 e to the minus 2x, I think. Because I get lambda squared plus 3 lambda plus 2, which factors into lambda plus 2 times lambda plus 1. Gives me those roots. Then I plug that into here, and I get z prime prime plus z is equal to minus c1 e to the minus x minus 2c2 e to the minus 2x And so this suggests a particular solution, Zp, of a e to the minus x plus b e to the minus 2x, which, by the way, gives me Zp prime prime is a e to the minus x plus 4b e to the minus 2x. So you add these, and you get 2a e to the minus x plus 5b e to the minus 2x is equal to this stuff. And that gives us a is equal to minus c1 over 2, and b is equal to minus 2c2 over 5, right? And then, of course, I've got the homogeneous solution because sines and cosines for z. So z is equal to c3 cosine x plus c4 sine x minus c1 over 2 e to the minus x minus 2c2 over 5 e to the minus 2x. And the y is just equal to c1 e to the minus x plus c2 e to the minus 2x. And that's how you'd solve this. Yeah. As you can see, they're coupled. The solution of y and the solution of z are intertwined because the differential equation for z also involves y. It's not surprising. So it is true for a given system, it is sometimes more convenient, in fact more economical, to simply use what we already know to solve. That's true. I shouldn't take that away from you guys. In fact, you can also play games with operator factorizations. If you look at chapter 5 of Nagel, Saff, and Snyder, they do things with basically elimination of variables by writing operators and essentially annihilator methods for systems. They multiply systems of differential equations once they've been written in differential forms by the appropriate annihilators to eliminate forcing terms and then add them. But it's a subtle business, these kinds of arguments. What I'm about to show you for the first order case and the general problem is far more orderly. But of course, for specific problems, it may be that some of those ad hoc methods about substitutions and direct operator arguments might be more efficient. That is true. You guys got this? A problem. Oh, do you have this? What did you not have? What didn't you get? Did you have this? Okay. So I've just been writing, and I've been talking to myself and writing off the screen for like a minute. Yeah. I know. It's hard to focus on the like moving this stuff around when all we can think of is watching movies with our special someone. I know. It's understandable.
Don't worry, I'll go with them to like.
You're gonna be chaperone. Very good, Landon. So now we're going to trade. We're going to be a little bit more abstract here. So let's let x1, x2, xn be unknown functions, yet unknown of time t. All right, and A is a given n by n matrix of constants. All right, real matrix of constants. And then F, I'll put a vector on it, is again a given function of t, all right? So the generic problem we'd like to be able to solve is dx dt equals to ax plus this force F. Now, let's set F equals to 0 for now. So if we have dx dt equals to ax, then this is the homogeneous problem, right? Well, I'm defining it, so you have no choice but to agree with me. It's a definition. Like, that definition is wrong. Sorry.
That's possible, isn't it?
I don't know. It depends on how much authority you have in mathematics. If you're Gauss and you tell me that the definition is wrong, I probably have to listen to you. I don't know. Oh, excuse me.
But
Okay.
If like a top student, two students.
Well, I don't know. Depends on who they were. So basically the thing here is we can use, I'm just going to go full bore. Define the matrix exponential, e to the at. Well, let's forget about the t for a second here. How about e to the b? This is I plus b plus 1/2 b squared plus da 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 da. All right, so more specifically, this is the sum n equals 0 to infinity of b to the n over n factorial. I prove that this series converges for arbitrary matrices in various notes that I have. The argument is simply this: if you look at the norm of this matrix exponential in terms of the matrix norm, which you can define, you can prove that it's a Cauchy sequence, but because this space of matrices is complete, it has to converge. Yeah. I is the identity matrix, right. Now, of course, there are nice properties for the matrix exponential. In particular, e to the b times e to the minus b is e to the b minus b, which is e to the 0, which, by the way, is I. So therefore, e to the b inverse is just equal to e to the minus b, right? Therefore, the determinant of e to the b is not equal to 0 for all b. Thus, I don't know, my s became an e somehow. Thus, e to the b has n linearly independent columns, which is pretty nice, right? Now, the calculus. What's the calculus for the matrix exponential? The calculus is really nice. So suppose we think about the mapping t maps to e to the ta. Now, if you want me to be specific here, what are we talking about? I mean, this is, if we write exponential for the map, this exponential is mapping from the reals to n by n matrices, right? You could say, well, I have never studied the calculus of such things. Well, fine, fair enough, you will soon. We are now. In short, you do it component-wise, all right? You just differentiate them one at a time. And long story short, the rules for the calculus of such functions, it's really just the usual thing. We have to respect the matrix algebra. So for example, an example of this calculus, something like this: d dt of a times b. The product rule would be dA dt b plus a dB dt. I must be careful to keep the order like that, otherwise it's not right, and that's matrix multiplication, so it doesn't commute, all right? Now, I don't think we actually need all that for this. If I want to differentiate e to the ta, right, what I get then is, well, I'll do it with the plus dot 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 notation. It's easier to look at that way. Of course, we could do it with a summation notation. That would be also fine. All right, so that gives me a 2t over 2 a squared plus 3t squared over 3 factorial a cubed. So you can factor out an a. What you got is 1 plus 1/2, 1 plus a times t, plus 1/2. 3 over 3 factorial gives me 2 factorial, right? Or 1/2, t squared a squared plus da da da. I mean, what is that? Well, that's, yeah, a to the ta, right? Oh yeah, the identity matrix, to be clear, yeah. Of course, it might be good for me to do that with the summation notation. So ddt. I dropped the 0 because it's 0 up here, and of course then this is just relabeling with n minus 1 in the place of n, so that's the matrix exponential again. So okay, but you're like, that's wonderful, but what are we trying to do? Let me bring us back to what we're trying to do again. We're trying to solve. So Bailu, can you come back over here? Is it still over here? We're trying to solve this, all right? dx dt equals ax. Now, there's a theory for systems of differential equations which I haven't shared with you guys, right? I'm just going to summarize the results. They're very similar to ones we've already seen. The general solution to this problem consists of n linearly independent fundamental solutions. So, to solve this, all I have to do is find those n linearly independent solutions. Because the matrix of coefficients is constant, I know that the solution is going to exist for all t. So what I'm looking for is dx1 dt. Oh, but you see it's an unfortunate use of 1. So this is vector x1 versus x1, all right? So understand x1 vector is not the same as x1. x1 is the component for the, I don't know, whatever. So it's people write double indices here for this reason. Anyway, but you need this to be true for I equals to 1, 2, n. I need to find n solutions somehow. Now, there's a very interesting bit of matrix math here. If I were to, say, concatenate these equations, if I was to write ddt, right, of these solutions, x1, x2, xn, like that, right? Then the differentiation is, the derivative of a matrix is the derivative of each column stacked just the same. So that would be dx1 dt, all the way on out, dxn dt, like so, right? But if these are solutions, if these are separately solutions, then each one of those is ax1 all the way on out to axn. Now you guys remember the concatenation proposition from linear algebra. You know that we can factor that a out. So you see, and in fact, what I'm really getting at here is not just an implication. I'm really getting at an if and only if thing here, which is that if you have a matrix such that the derivative of the matrix with respect to time is equal to a times the matrix again, that's true if and only if all columns of x solve dx dt equals to ax. See that? So I can trade solution, the notion of a solution at the level of a column. I can be greedier. I can say, I don't want to think about one solution, one column vector solution. I want to think about n of them all at once. That's the viewpoint of the matrix of solutions, right? Now, if that matrix of solutions is linearly independent, then the general theorem says that the theory tells me that the general solution, x of t, can be just written as the matrix of solutions at time t times some constant vector c, because that is nothing more than like c1x1 plus plus cnxn. Right? So to find a matrix of solutions which is also containing n linearly independent columns is to solve this system. But guess what? We already did that. Right? Because I just invented this matrix. I didn't invent it, but Someone invented it or discovered it. Hey. This matrix exponential. But this matrix exponential is just such a thing, right? Here's the matrix X. Here is A times X again, right? It's a solution matrix. And because the determinant of e to the ta is not equal to 0, that means it has n linearly independent columns in it. We solved it. The solution is simply, and isn't this beautiful that it's so simple as this? That the solution, look at this, is just x of t is equal to e to the ta times the constant vector c. It's just like when we have y prime equals to ay, we get solution y is equal to, e to the ta times some constant c. Of course, we don't usually write the c over here, but what could be more natural? And so you see why you'd look for this notion of matrix exponential. On the basis of this analogy alone, you'd look for it if you had time on your hands. Now, you guys are well aware, though, that this isn't the end of the story. It remains to see how do you actually calculate this. I mean, that's an infinite series of matrices, right? So unless your matrix is nilpotent or something nice, it's really hard to directly calculate the matrix exponential. That is where eigenvectors and generalized eigenvectors come into play. Because eigenvectors and generalized eigenvectors allow us to extract those n linearly independent solutions in a nice way. Yeah. You gotta go. Oh man. Well, this part I already showed you. In this part, yeah, this part we actually saw in linear. So, okay, cool.
We need to have decide what you're going after. Like over this is another part you're going to go over tomorrow.
Yeah. Tomorrow we'll do Laplace transforms.
Okay.
That's the end.
Before that.
Yeah, in the morning.
In the
Is that
morning?
okay? Okay.
Like 10.
Is 10 good? Okay. Yeah, 10.
All right.
What? You look confused. No, we're not done today yet. Let me wrap up the systems here. I still need to do the. I need to talk about eigenvectors, generalized eigenvectors, and I also need to talk about how to find the particular solution. I didn't do that yet. Okay, so the eigenvector, right? So you look for a solution to A minus lambda I, and I traditionally use U here because I'm using X for the solution to the differential equation. So A minus lambda I U equal to 0 for U not equal to 0 makes U an eigenvector with eigenvalue lambda, right? And then, so if you look at what happens then, and then on the other hand, we have generalized eigenvectors, right? What's the generalized eigenvector? We arrange them in chains. Yes. What on earth did you do? So we have A minus lambda I, to the, let's say, times U, say J is equal to U, J minus 1. So, for example, if I have just two of them, if I have like A minus lambda I times U2 equals to U1, and I have A minus lambda I times U1 equals to 0, then this will be a chain of length 2, right? Generalized eigenvectors. Length 2. As we discussed in linear algebra, you can find these things. You can find a basis of generalized eigenvectors for any, certainly for any matrix with real eigenvalues. If we don't have real eigenvalues, we've got some complex eigenvalues, and we've got to find complex eigenvectors. But then the real and the imaginary parts of those make something really nice happen. So we could still use the complexification technique to rip out solutions in that case. Anyway, let me make my point here. What does that have to do with the matrix exponential? Well, the matrix exponential has this wonderful identity called the magic formula. E to the TA is e to the what? We could do TA minus lambda t minus lambda ti plus lambda ti. Oh, by the way, the eigenvalue, in order for there to be a non-trivial solution to that equation up here, right? We know from linear algebra that lambda has to solve what? Yeah, it must solve the determinant of. Yeah, maybe t is a better thing to use, right? A minus. Oh, t is kind of a bad choice here for other reasons. Let's use. Oh, x is kind of used. Oh man, what to use? I don't know. Alpha. Alpha I equals to 0. So if you put alpha equal to lambda, it should be the case that. Oh man, come on. Just all around bad. Anyway, it must solve the characteristic equation. All right. So. Lambda can't just be any old constant. It's very specific to the matrix involved. But I can add 0 here. And then the cool thing is this is a multiple of the identity. That means that this matrix commutes with that matrix. So the laws of exponents work. More generally, there's something called the Baker-Campbell-Hausdorff relation. But, I'll leave that for another day. This is e to the lambda t times the identity matrix. That's an identity that this is equal to that. And then this, well, I've got e to the t times a minus lambda I. Right? And so then I can just, the definition of the matrix exponential, this gives me e to the lambda t times I plus t times a minus lambda I plus t squared over 2, a minus lambda I quantity squared plus t cubed over 3 factorial, a minus lambda I cubed, and so forth and so on. The beautiful thing about this identity is it shows you how to take the right linear combinations of the matrix exponentials columns in order to get solutions that we can really wrap our mind around and grasp without ever actually calculating that infinite series of matrices with which we've defined e to the TA. In particular, you see what happens when you hit it with an eigenvector, right? When you hit it with this, if you have a minus lambda I times u1 equals to 0, that tells me that e to the TA times u1, well, you see what happens when u1 hits this, it's 0. When it hits this, it's 0. When it hits that, it's 0. Everything's 0 except for that term. So we're just left with e to the lambda t times u1. That's the first kind of solution. I would call this an eigenvector solution. You can think of that as being the x1 in the fundamental solution set. And then if you have a minus lambda I times u2 equal to u1, well, then when we calculate the matrix exponential e to the at times u2, are you getting this, Belu? Down here? Okay. Well, what happens? Of course, by the way, if you can easily see from this that a minus lambda I squared on u2 is what? That's a minus lambda I on u1, which we assumed is 0. So like these squared terms or cubed terms and all on the way out, that all truncates to 0 for this generalized eigenvector of order 2, u2. The only thing that remains is this term and this term as multiplied by u2. Of course, the I gives me back, e lambda t is up front, I times u2 gives me u2, and then since a minus lambda I acting on u2 gives me u1, I just get plus t u1. Right? And so forth, right? If I had a generalized eigenvector, if I had so forth and so on, if I had a minus lambda I, if I had a chain of length k, let's say, what would I have? Well, I would have e to the lambda t out front. Then I would have u to the k. That's my first thing. Then I would have plus t, uk minus 1, right? Plus t squared over 2, uk minus 2, and so forth and so on until I got to what? 1 over k minus 1 factorial, t to the k minus 1, and my eigenvector at the bottom of the chain, u1, or the top of the chain, depending on how I look at it. So I can find these chains of generalized eigenvectors for an arbitrary, yes, Bailey? What? You have to leave? Why? Tutor? No one needs your help. They don't pay you enough. They don't pay you enough. Forget about them. Okay. Well, it's fine. Thanks, Bailey. Yeah, we'll be fine. We're almost done. Yeah, you can come. We're having the Daniel's party. So, not that Daniel. Let me call you back about that. I'm not sure. I got to talk to Jenny. You can now pan over here. So that's how we find a fundamental solution set, right? We can calculate we can extract solutions from the matrix exponential by simply multiplying by eigenvectors or generalized eigenvectors, and that will get us a solution. Now, in the case we have a complex eigenvector, right? If you have e to the at times, suppose you have like a minus lambda I times u equals to 0 for lambda equals to alpha plus I beta, and u equals to a plus ib, right? So in other words, we have a complex eigenvalue. Yeah, thanks Daniel. Then in this case, the magic formula still holds true, all right? But now it's a complex equation. What's wrong? Oh, okay. Oh, it does that, yeah. So when it was the same calculation holds true, right? I still have that e to the ta times u is a solution, right? But now it's a complex solution is the thing. And so what I really have then is e to the alpha plus I beta times a plus ib, where I'm assuming a vector and b vector are real vectors, right? That's a complex solution, right? And so you could say, I could call this thing z for the moment, right? And so the real part of z and the imaginary part of z, these will be separate real solutions to dx dt equals to ax because of the complexification theorem, right? I mean, it's again this. We find a complex solution. There are two linearly independent real solutions hidden in there. And then all you got to do is just multiply this thing out, right? So Euler's formula, we get e to the alpha t, and you get cosine beta t plus I sine beta t, parentheses, times a plus ib. And so what that gives